Hello, in this video we're going to talk a little bit more about equilibrium constants and how you treat them when you work with reactions in different ways. So we talked about this in a previous video, and here's what we said, is that if you have some chemical reaction, and so here's the example we used, you have the products on top, the reactants on the bottom, multiplied to a power of their stoichiometric coefficients. Then if you reverse that chemical reaction to get something that looks like this, then you're going to invert the equilibrium constant. And if you look at this new equilibrium constant in red, the form of it, it matches our newly reversed reaction. So this makes sense based on how equilibrium constants are put together. Now the other thing we said is that if you multiply a reaction uniformly by some coefficient, then your equilibrium constant is taken to the power of that coefficient. So in this example, if you multiply all the coefficients by 1/2, then you take the old equilibrium constant to the power of 1/2, and then that gives you your new equilibrium constant. Okay, so that's old news. The new news is what happens if you have multiple steps together in some sort of process that's an equilibrium process. So our super simple example here is we take A and B, which goes to now an intermediate, C plus D. Then we take that intermediate and do it in the second step to make E and F. And at the moment, we don't care about kinetics, so we don't care which step is slow, which step is fast, etc., etc. Now, if you write the equilibrium constants for both of these, I'll call this first one K prime, and the second one K double prime. Now, this matches what we would expect from these two equations. So now the overall reaction here is written like this. A plus B goes to E and F. And so how do we get the new equilibrium constant for this overall reaction? And well, it's the product of the equilibrium constants of each of the constituent reactions. So if you add reactions together, your equilibrium constant is the product of the equilibrium constants of those reactions. The reason this works is if you take each of these original equilibrium constants and multiply them by each other, well look, the C and the D are going to cancel out, and then you're left with what you would expect for this overall reaction. And so it looks a little something like this. And so, yeah, so if you take two or more steps and add them together, then your equilibrium constant of the overall is just the product of all those individual equilibrium constants. Okay, just another thing to know. So the kind of problems we can do based on this are, they look really much like Hess's law problems that we talked about in the first semester of general chemistry, where you add these reactions up and then figure out what the overall enthalpy change is for this reaction. So here we're taking the same idea, trying to get these two reactions to equal the third one on the bottom. But now we're given equilibrium constants, and we want to see what the equilibrium constant is for the overall reaction. So when I do these kind of problems, the first thing I'm looking for is, well, let's see here. I need some sulfur dioxide up in my eventual reaction. And, well, the only place sulfur dioxide is present is right here. So that means, well, this is a product up here, but then it's a reactant down here. And so that means I need to reverse this reaction. So let's do that and then see what it gets us. Okay, now when we reverse this first reaction, remember we need to take the inverse of the equilibrium constant. So we do that and get our new equilibrium constant for this first reaction. All right. Now let me scoot this up. And then you can do this two ways now with this particular problem. One, you could multiply both reactions by 1/2 and then add them together. Here I'm going to add them together as is and then multiply it by 1/2. So we're going to add both these reactions together. And well, if you look at it, the oxygen cancels out on both sides. And then we're left with this overall reaction. And then for this overall reaction, the equilibrium constant is now the product of the equilibrium constants of the two reactions we added together. All right, almost there. So then this reaction here that's on the bottom, that one is now uniformly multiplied by 2 compared to the original reaction that we're trying to find. And so to get rid of that, we multiply all these coefficients by 1/2, which means we need to take our equilibrium constant for this reaction and take it to the power of 1/2. And so if you do that, you get 78. And this is now the equilibrium constant for this overall reaction that we are aiming to try to get. So, yep, just a short little video to show you this trick. Thanks for watching.